That beautiful music was Chopin's Fantasy Impromptu, and I hope today's lecture will help us understand that a little bit better. So far, all the lectures we've talked about so far have been really about a single topic, and that's pitch. Today, we're going to talk about rhythm. Imagine music without rhythm, or more precisely, music without any change in rhythm. Think about what that would be like. It's one of the most famous melodies in all of classical music. It's Beethoven's Fifth, but the character is completely lost because there's no rhythm. This motif, this repeated pattern, the falling of a major third. It's supposed to represent fate. Without rhythm, there's like no drama, there's no suspense, there's no life to it. When you put rhythm in, even just on a violin, oh, it's like fate is knocking on your door. Oh. Well, that was music without rhythm, and that's why it's so important. What is music with only rhythm? Can rhythm alone be music? Well, certainly percussion instruments, they alone can play music, but nearly all percussion instruments have different pitches. Timpani, xylophones, drums, or at least different timbres. Think of a bongo or a bass drum. And they all have at least volume. Can pure rhythm with no pitch, no recognizable overtone series, can that be music? You know, think of clapping. Or maybe if you're thinking about percussion instruments, think about a rim shot where a percussionist will hit the stick on the edge of the drum instead of the head. There's actually a famous modern piece that answers this question with an emphatic yes. More on that in a minute. First, I want to see if we can find a definition of rhythm. Now, definitions in math and music, you know, some words just sort of defy definitions, but we use them all the time anyway, and somehow we're comfortable using them even though we don't have a good definition. In mathematics, you know what points, lines, and planes are, but mathematicians have really struggled to give those good definitions, and sometimes we just take those as axioms, sort of undefinable primaries. We agree what they are without definition, and we all sort of assume that everybody around us is using the same implicit definition. Mathematicians also, for centuries, used things like dimension, function, all of these without definition, infinitesimal, convergence, infinity. In music, we've actually already seen one sort of undefinable or very difficult to define term, timbre. Remember, one definition was actually negative, what it's not, and the other definitions just told us what it allowed us to do, to tell a flute from a violin. Today, we're going to talk about another musical undefinable, and that's rhythm. Now, you might think you know what rhythm is, but if you look to the Grove Music Dictionary, it actually quotes Kurt Sachs from Rhythm and Tempo. This is what he said. What is rhythm? The answer, I'm afraid, is, so far, just a word. A word without generally accepted meaning. Everybody believes himself entitled to usurp it for an arbitrary definition of his own. The confusion is terrifying indeed. Wow. For us, sort of like a point or a line, we know what it means. Rhythm is sort of, regularly ordered pattern of durations and strengths of notes, and we'll just sort of understand that to be the definition. Let's go back to this question, what is music with only rhythm? So Steve Reich was born in New York in 1936. He grew up in California and he studied at Cornell and at Juilliard, and then he traveled to Africa, to Ghana, in 1970. He wrote clapping music in 1972, and that really answers this question. He was bringing some of the African rhythms he had learned to Western music, and he was using only the human body. The piece is written for two clappers, and they're both clapping the same 12-beat phrase, but one drops a beat behind the other every 12 bars. The entire piece takes about 3 minutes. It's a fairly long thing, and you can see it on YouTube. There are lots of different versions, including Evelyn Glennie, who does it both parts by herself, which is really impressive. So here's a short piece that I composed to give you an idea of these ideas. These ideas in this piece are really highly mathematical, and I'm pleased to welcome associate producer Chris Stoner to help me with this piece. Welcome, Chris. I'm calling this piece Music Without Pitch. Thanks very much. I'm not sure what you're supposed to do at the end of a clapping piece, if you're supposed to applaud again. Thanks. So, is that music? I think that really depends on your own philosophy. For me, that is definitely music. It's sound and it has an aesthetic sensibility. For me, that's enough. Now, before we dive into Western music, first I want to take a little bit of a diversion. Rhythm plays a role not only in music, but also in something like poetry, because words form a rhythm. Indian poetry provides some really interesting connections between rhythm and mathematics, and I want to turn to that next. Indian poetry was traditionally written in Sanskrit, and it has two types of words. There are short syllables and there are long syllables. And the long syllables are exactly twice as long as the short ones. So I don't read Sanskrit, but it might be something like long, short, short, long, short. Now, Pingala was one of these poets, and he lived several centuries before the Common Era. He asked an interesting question. How many different ways are there to put short and long syllables together to get a line of a given length? If you're thinking musically, you could ask, how many different ways can you put 1 and 2 beat notes together to get a rhythm n beats long? Let's do some quick examples and see if we can figure this out. We can represent this graphically or, in fact, musically. You can think about like squares and rectangles, or you can think about rhythms. We could write it out in musical notation. If you're writing around something 1 beat long, you have only one choice, just a short syllable. If it's 2 beats long, you could do short, short, or you could do long. If it's 3 beats long, it turns out there are 3 ways. You could do short, long, you could do long, short, or you could do short, short, short. If you know musical notation, you can write this out in half notes and quarter notes. 4 beats long, there are 5 ways of doing it. 5 beats long, 8 ways. 6 beats long, there are 13 ways of doing this. Let's look at those numbers. Let's look at those answers that we just got. What's the pattern in there? I think we've seen these numbers before. Those are Fibonacci numbers. Each one is the sum of the previous 2. 8 is 5 plus 3. 13 is 8 plus 5. The next number has got to be 21, 13 plus 8. The poet Pingala, and later other Indian poets, Virahanka in around 700 AD, and Hemachandra around the 12th century, they discovered what we now call Fibonacci numbers. Fibonacci was another name for Leonardo da Pisa. He published his work early in the 13th century, long after the Indian poets. That's a theme we'll run into a lot. We call it something after one person's name, but that wasn't the first person to come up with the idea. I'll leave this as a question for you. Why is it that the number of ways to write a 12-beat long rhythm is equal to the number of ways of writing a 10-beat long rhythm plus 11? Why is it that we get this pattern, that the next one is the sum of the 2 previous ones? It's an interesting question to think about. Of course, this happens a lot in mathematics, so some question arises in some field other than mathematics. In this case, it was poetry, and we build some mathematics up to answer it. And then mathematicians go off asking many more questions that you didn't actually need in order to solve the original problem, but we just think it's really beautiful and fun. You could ask, what if you included longer words? Say, what if you had words that were 1, 2, or 3 beats long? What if you're only allowed to use so many longs? What if you can't put more than 2 short syllables together? Here's another question. To get the answer for n beats, do you have to figure out all the ones before it? You know, we think of the answer for n beats as the answer to the previous 2 questions, n minus 1 and n minus 2. But do you actually have to figure out all of those in order to get the nth one? I'll answer this last question for you, even though you might not believe it. The answer is no, you don't have to get all the previous ones. We have what mathematicians call a closed form solution for this. We can give you a formula which gives you the number of ways of using short and long syllables to form an n-beat phrase. It's called Binet's formula. And here's Binet's formula. Yes, I know. So the answer has to be a natural number because of the way we phrase the question. And this formula doesn't look like it would give you a natural number, but amazingly, it actually does. Of course, like the Fibonacci numbers, Binet was not the first person to discover this either. So let's go back to Western music, and let's talk about a little bit of notation. So a whole note represents 4 beats, and it looks like this. A half note is 2 beats. Here's one of them. A quarter note is just 1 beat, An eighth note is a half a beat, a 16th note is a quarter of a beat, and so on. When they're grouped together, some of these look slightly different. Sometimes we use bars instead of flags when they're grouped together. We can make rests, for silence, of the same length of any of these notes, and they look like this. If we want a note that isn't a fraction with a power of 2 in it, we can use other notation for that. We get things like triplets or quintuplets. Now each of these is exactly one beat, but it's no longer divided in half or fourths or eighths. And one more thing, if we add a dot after a note, it adds half of the length of the note. The same thing works with rests. But if we had a dotted half note, the half note has 2 beats, and then the dot adds an additional 1 beat, which is half of 2. So a dotted half note has 3 beats. So we have to split these up. We can't have notes, 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 notes. We split them up sort of like we split up English language with sentences. And in order to do that, we need to know how many notes to put in a particular measure. And we use a time signature. It actually looks suspiciously like a fraction. If we were doing something in 3/4 time, each measure has 3 beats. That's the top number. And each beat is 1/4 long. That's the bottom number. Let's see a simple example in 4/4. It's called common time. It's 4 beats per bar, and each beat is a quarter long, a quarter note long. That's why we get the names of the notes, the whole, the half, the quarter, things like this. So this is a version of Twinkle, Twinkle, Little Star, the first piece I ever learned. And you can see how the note lengths are used in that phrase. There are a lot of standard time signatures. 3/4 is a very common one, 3/4 notes per bar. Most waltzes are written in 3/4. 2/4 is also another common time, 2/4 notes per bar. 2/2 is sometimes called cut time or alla breve. 2/2 would have 2 half notes per bar. 6/8 is another one. 6/8 notes per bar would also be quite common. Now you notice that the top number here can be any natural number where the bottom has to be a power of 2. And you can do that in any combination. And modern composers make more use of stranger options. Here's a measure of 7/16 that I played. It was in the piece I played back in lecture 5. 7/16 notes per bar. Now some of these time signatures are a little bit more interesting mathematically than others. One of the particularly interesting ones is groups of 6, for instance 6/8 time. Now the reason 6 makes things interesting is because 6 is 2 times 3. It's the product of 2 different primes. And so you can think of 6 as 2 groups of 3, or you can think of it as 3 groups of 2. Musically, 6/8 sometimes feels like it's 2 groups of 3, triplets, 1, 2, 3, 1, 2, 3. And sometimes it feels like it's 3 twos, 1, 2, 1, 2, 1, 2. Probably the most famous example of this is Bernstein's West Side Story. The song is I Like to Be in America. I like to be in America. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Works just like that. And so you see how what he's doing is he's grouping those 6 beats either in groups of 3, 1, 2, 3, 4, 5, 6, or in groups of 2, 1, 2, 3, 4, 5, 6. Related to this are hemiolas. Now hemiolas are a particular musical figure that are heard in a piece in which every 6 beats are usually grouped into 2 groups of 3. And then the hemiola comes when those 6 beats are grouped into 3 groups of 2. The hemiola comes from the Greek, that's the name. It means 1.5, and that's the ratio of the length of the groups of 3 to groups of 2. A hemiola is used extensively in Western classical music, especially by Handel, but also Brahms, Dvorak. Many composers use this sort of figure. The effect of using a hemiola is that it interrupts the normal flow. You sort of catch the listener a little bit off guard. If you haven't studied music, it's a little bit subtle, and so I'm going to work hard to try to help you hear this. So let's hear an example from Handel's Water Music of 1717. Now, the Water Music debuted in front of King George I on the Thames. And the orchestra was actually seated, about 50 of them, on a barge in the river. That's part of why it gets the name. And this piece makes liberal use of hemiolas. In every one of these movements, you can hear some sort of hemiola. And we're going to listen to a little bit from the movement called Hornpipe. It's the second movement from Suite in D major. The main theme has groups of 3, 1, 2, 3, 1, 2, 3. And you'll hear 8 groups like this. And then after that, you'll hear the hemiola, where instead it's grouped in 2, 1, 2, 1, 2, 1, 2. We're actually going to listen to this twice. And first, I want you to listen to where the emphasis is, and I'll count along. Listen for the hemiola, where the emphasis comes every 2 beats instead of every 3. It goes from, if you're counting in 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And then it switches to 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. I'll count this just as 1, 2, 3, and 1, 2 to tell you that it's groups of 3 or groups of 2. And even if you can't read music, we'll try to help you follow this with the visuals. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 1, 2, 1, 2, 1. Let's listen to that one more time, and this time I'm not going to count along. Listen for the effect of the hemiola. By using this hemiola, Handel is signaling that something is changing. The end of the phrase is coming. He's interrupting the previous pattern, and he's trying to catch the listener a little bit off guard. Let's listen to that again. Now you might ask a very mathematical question. Can we do a hemiola type thing with other numbers other than 6? Remember that hemiolas work because 6 is 3 times 2, but it's also 2 times 3. And that's why we get 2 groups of 3 or 3 groups of 2. You might try to find other interesting combinations, like 8 is 4 times 2 or 2 times 4. But the groups of 2 would fit nicely inside the groups of 4, so that wouldn't be very interesting. If you did 10, which is 5 times 2 or 2 times 5, those are fairly long groups of notes to think about. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you would switch in the hemiola part to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a lot of notes in there. Now you might think about doing 12 as 3 groups of 4 or 4 groups of 3. There are a lot of these numerical games that you can play with rhythms, and you can hear a lot of these on David Brubeck's wonderful album, Time Out. He does a lot of interesting mathematical stuff with rhythm. Next, I want to switch from a single part doing different rhythms to 2 different parts. And these are called polyrhythms, if you have 2 parts and they're playing different rhythms. And the opening music, the Chopin that we heard, uses polyrhythms to give it this characteristic sort of agitated, unsettled feeling. Let's dive in and try to understand polyrhythms. And I need to tap in order for you to hear these. So let's do a really easy polyrhythm first. We could have 4 against 2, right? So we could write this in common time, 4/4, and we could think about it as 4 quarter notes in one part and 2 half notes in the other. So with my right hand, I'm going to do the half notes, 1, 2, 3, 4, 1, 2, 3, 4. And with my left hand, I'm going to do the chord notes, 1, 2, 3, 4, 1, 2, 3, 4. And I can actually emphasize one hand versus the other by letting my wedding ring here hit the wood, 1, 2, 3, 4. That's much louder than this. So this is what it sounds like when you put them together. And here's the 4. Let's do something that's just a little bit different. Let's do something in 3/4 time. This is also fairly easy. We're going to have, my right hand's going to do 3 beats, going to do one beat per bar. 1, 2, 3, 1, 2, 3. And my left hand is going to do 3 beats during that period. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And again, that's fairly easy. You can hear the 3 clearly. 1, 2, 3, 1, 2, 3. When musicians first learn to play things like this, we call them triplets, the common mnemonic is to say some sort of berry, like strawberry, strawberry, to get them nice and even. Let's look at something a little bit more interesting. Let's look at 3 against 2. So now my left hand is going to do 3 notes again. 1, 2, 3, 1, 2, 3. But during that same time, during each one of those groups of 3, my right hand is going to do 2 even beats. 1, 2, 1, 2. And now we get something where they don't quite fit together. This is sort of like a hemiola, except now instead of playing them sequentially, we're actually playing them simultaneously. Here's what it sounds like. You might hear a little bit of the rhythm from Carol of the Bells, Or sometimes people say hamburger bun, hamburger bun. There are other mnemonics that people use. But let's listen to that, and I'll bring out the 3 using my wedding ring again. And here's the 2 on my right hand. And you can see how those are going on simultaneously. Let's look at some musical examples of this. One of the more famous comes in Tchaikovsky's Piano Concerto. This is one of Tchaikovsky's most famous pieces, and the time signature is 3/4, 3/4 notes per bar. The piano is in 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. But the strings end up being in 2. They're playing 2 notes for every 3 of the piano. 1, 2, 1, 2. The rhythm in the piano is actually a little bit more complicated than just 3. Instead of going 1, 2, 3, 1, 2, 3 like this, the rhythm is like this. 1, 2, 3, 1, 1. I remember the first time I played this, we were rehearsing without the piano soloist, and the conductor is conducting in 3. 1, 2, 3, 1, 2, 3. But then the entire orchestra is playing in 2, and it looks sort of like this. 1, 2, 3, bum, 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 bum. It's a weird effect when you're not playing in time with the conductor. Let's hear it with the correct pitches. Before we hear the real music, I'll play it on my violin, and I'll play the piano part as well. Here's the piano part that you're going to hear. 1, 2, 3. Whew, I messed that up a little bit. The orchestra behind them are playing the following. Instead of playing 3 beats per bar, they're playing just 2. So while the piano is going 1, 2, 3, 1, 2, 3, the orchestra is doing this. I'll try to keep time with my foot. 1, 2, 3, 1, 2, 3. And then it goes on like that. So let's listen to this piece of Tchaikovsky. And while we listen to this, I'm going to count us through it. So the first time I'll count with the piano part, and that's going to be in 3. Let's listen to that. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And now we're going to hear the same thing again, except now I'm going to count with the orchestra. They're playing in 2. They're playing 2 evenly spaced notes in the span of 3 of the piano's beats. Let's listen to that. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And finally, let's hear it without me counting out these beats and see if you can go back and forth in your mind, sort of following the piano's 3 beats. 1, 2, 3, 1, 2, 3, and then switching and listening for the orchestra into bum, 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 like that. Let's hear that together. Now let's hear it in a larger context of the piece. Now the lead into this section actually has 2 hemiolas right before the 3/2 section. So before we listen to the entire thing, let's listen to just the hemiolas. And I'll count along to highlight when it goes from groups of 3 to groups of 2. Let's listen to that. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1. And then it goes into the 3 versus 2 section. So now let's hear the entire passage. I'm not going to count anything, but you'll hear it definitely in 3, and then you'll hear the hemiolas, and then finally you'll hear the 3 against 2 polyrhythm. So you might ask a natural question, why is it that composers use polyrhythms? Let's talk about that for a minute. when you use polyrhythms, you get this sort of sense of instability. You get sort of a sense of turning around, unsettling, before resolving back into a normal rhythm. The two rhythms sort of form two competing forces, and you get this rhythmic tension. And then finally, you release that rhythmic tension when they fall back into line again. Now, last time we were talking about tension with pitch, right? That was dissonance. And today we're talking about tension with rhythm. There's also a mathematical question. How do you calculate polyrhythms? You know, if you have 3 versus 2, what you're doing is one part is dividing something into 3 equal parts, the other is dividing that same time into 2 equal parts. It's actually a lot like adding fractions. You need sort of a common denominator. You need some sort of equal spaced piece that you can divide this measure into. And so if you have 2 versus 3, you divide that bar into 6 equal parts. That's the right sized piece so that you can split that into 3 and you can split it into groups of 2. If you were doing P versus Q, it would require dividing the time into the least common multiple of P and Q, right? That's exactly what you would need to do if you were adding the fractions 1 over P and 1 over Q. So let's look for a second at 3 versus 4. So I want to demonstrate this for you first. So my right hand is going to do 3 beats. 1, 2, 3, 1, 2, 3. And my left hand is going to do 4 beats. 1, 2, 3, 4, 1, 2, 3, 4. All in the same span of time. There's actually a phrase, a mnemonic to help you remember how to do this. It's pass the gosh darn butter, pass the gosh darn butter. And now I'll demonstrate so you can more clearly hear the 4 and the 3 with my wedding ring again. Or to emphasize the right-hand side. Now, if you want to write this in music, what time signature might you use? Well, the easiest way to do it is in 12/8. But alternatively, you could write the same pattern in 6/8. You could even sort of use this triplet notation that we talked about earlier to write it in 4/4 or 2/4. So now, I want to hear how Chopin used 3 against 4. And to hear that, let's go back to the piece we were talking about earlier, the piece we heard at the opening. You see, Frédéric Chopin, he was a French and a Polish 19th century pianist. He was also a composer, of course, and he was a master of the keyboard. He really revolutionized fingering on pianos. He wrote Fantasy Impromptu, the piece we heard at the top. That was in 1834. And the tempo marking for this piece, in Italian, of course, is allegro agitato. Now, the allegro means lively, joyful, but the agitato means agitated, unsettled. The agitation here is created by this polyrhythm, 3 against 4. Now, it's written in 4/4 time. There are 4 quarter notes in each bar. The right hand in this piece is playing 16th notes, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, in every beat. The left hand is playing triplets, 3 per beat, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So let's listen to each hand separately and slowly. And what I've done here is I've put this on a computer. And so you'll hear this piece, and this is just the right hand, and this is a computer playing it. And you can hear the groups of 4, 1, 2, 3, 4, 1, 2, 3, 4, like that. Now the left hand at the same time is playing triplets. So in each beat, they're playing 1, 2, 3, 1, 2, 3. So let's look at the left hand and see what that looks like. And this left hand, you can see the triplets. And again, we're going to hear it played by computer, so you hear it exactly and very precisely. Let's listen to that. And finally, let's listen to the left and the right together. Now remember that this piece is marked agitato. It's supposed to be agitated. And listen for the left hand playing the 3s and the right hand playing the 4s. Listen for the agitation caused by this polyrhythm, and listen how they match up every beat. They come back and sort of match up together. Let's listen to that. felt a little bit cold and sort of mechanical, and that's because it was played by a computer. So let's listen to a real pianist play this with feeling. And we're going to also add the first few opening bars of this piece. I want you to listen to how Chopin is using the mathematics of polyrhythms to create this agitated feeling, and also how the pianist plays with this rhythm, moving a little faster and a little slower to create a sort of emotional sense to this. And I hope we now better understand this piece and what we were listening to at the beginning of this lecture. So here again is Chopin's Fantasy Impromptu. It's such a beautiful piece. I'm sort of sad we can't take more time to listen to the entire thing. But let's move on to more complicated polyrhythms. So you might ask why and how you would play something like 3 against 5, or 4 against 7, or 5 against 11, or for that matter, P against Q for any numbers P and Q. 3 against 5, you would need 15 divisions. Again, P against Q would need the least common multiple, just like fractions. If you're trying to do 4 against 7, you would actually need 28 subdivisions. There's another mnemonic for that if you want to do 4 against 7. It's walk down the hall with a new tennis ball. And that's 4 on one side and 7 on the other. Now, some of these crazy polyrhythms are actually used. Let's look at how Chopin used some of these more exotic polyrhythms. In his Nocturne, Opus 9, number 3, in a span of just 5 bars, it's filled with polyrhythms. There are hard ones, 3 versus 5, 3 versus 7, 3 versus 8 even, but there are also some easier ones, 3 versus 1, 3 versus 9, 3 versus 6. Those all fit nicely, but something like 3 versus 8, that's very complicated. So let's listen to just these 5 bars and how Chopin is using polyrhythms. Let's also listen to one more sort of extreme example from the Grieg Piano Concerto. It's in the first movement, in the cadenza, where the orchestra drops out and it's just the solo pianist. In this section, the left hand is making runs 7 notes per beat, and the right hand is playing a melody plus 8 notes per beat. You know, if you wanted to do this exactly, you would have to divide each beat into 56 really tiny pieces. Here's what that sounds like. Of course, pianists don't actually think in those 56 little pieces. Pianists are actually just sort of learn to have their hands do different things. We could take polyrhythms to maybe their logical limit, and Charles Ives does a really excellent job of that. He was the son of a Civil War band leader. He was really famous for using church and traditional melodies. He wrote in the 19-teens a 4th symphony, and in addition to some of the polyrhythms we talked about, he actually requires the piano to be tuned a quarter step sharp. That's much more than the tuning I was doing in the last lecture. Orchestras actually usually use an upright piano. They don't want to hurt the soundboard on their nice 12-foot Steinway. Now, in the second movement of the 4th Symphony, the polyrhythms are taken probably to their logical extreme. They're so extreme that 2 different parts of the orchestra are in 2 completely different rhythms. In fact, 2 conductors are usually used to do this piece. One conductor sits quietly during the opening part, and then at some point the second conductor stands up and conducts part of the orchestra while the main conductor is conducting the other part. And at some point, the first part finishes and the second conductor sits back down and they finish the piece. So just to be clear, here's what polyrhythms are all about. The point is that it's a musical tool used to create a sort of unbalanced feeling with rhythm. And you're creating rhythmic tensions. Now, these are used throughout Western music, but also, for instance, in something like African drumming. There's a mathematical aspect to polyrhythms, and that's similar to fractions and common denominators. And for most performers, the mathematics is really implicit. Nobody's sitting there thinking about the little divisions in order to do that. You just learn to do these two things simultaneously. Polyrhythms are just sort of rhythmic tools. But what if we combined rhythm with pitch? So far, it was just rhythmic patterns, but if we add pitch, we can do some more interesting things. Now we're going back to just a single part, a single instrument playing. And you could think about playing a rhythmical pattern that's 5 notes long, something like this. 1, 2, 3, 4, 5. It's 5 notes long. It's 4 beats long. But you could also think of taking a pattern of pitches that's 3 long, maybe A, B, C. And now you could put those pitches with those notes, and you notice that the 5 notes and the 3 pitches don't match up, and so it sort of turns around, and it's a while before you get back to the beginning. But it would sound like this. And how often would it repeat? Well, you take the least common multiple of 3 and 5, you get 15. It repeats every 15 notes, and since there's 5 notes in each of these bars, it repeats every 3 measures. Musically, you get this sort of a sense of turning and turning before you return to the beginning. It's almost like you have 2 gears, and they have different sizes, right? And so one of them turns a lot more, and it's sort of every once in a while they mesh up perfectly, but then they sort of go out of sync again, and finally again they come back and mesh up perfectly. Let's hear some examples of this phenomenon. George Gershwin was born in Brooklyn in 1898. He was the younger brother to famous lyricist Ira Gershwin. He composed pop music, musical scores, classical music. He was all over the place. A lot of it was in the tradition of French composers like Ravel and Debussy. But he also brought in influences of jazz and folk music. In 1924, he composed what's probably his most famous piece, Rhapsody in Blue. It's a work for piano and orchestra, and at least recently, it's definitely his most heard work because United Airlines adopted it as their theme song. This piece makes use of these repetitious phrases again and again and again. So the first example that I'm going to play it's exactly what I was just playing. It's the same rhythm we had last time. It's one of the main motifs or patterns, and it gives you this sort of sense of turning. And it only repeats every 15 notes. And it sounds like this. Do you hear the sense of sort of turning and instability in that? It finally resolves when the rhythms and the pitches line up again. Let's hear one other example of a sort of a rhythmic pattern like this, and it's also from Rhapsody in Blue. Here we have 6 notes per bar, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. But it's an 8-note scale that's being played. The scale sounds like this. And so it's that 8-note scale, but it's wrapped in 6 pieces. And so it's going to repeat every 24 notes. That's every 4 bars. Every 3 times you go up the scale, they're going to match up again. So it's going to sound like this. And you hear that sort of rotation, that sort of instability. In Rhapsody in Blue, this happens near the end of the piece, this turning sensation. And the composer here is using it to build tension. There are lots of other examples that you can pull of this sort of rhythmic patterns. My favorite is actually not from classical music, but from a tune of Bill Withers, Ain't No Sunshine. You can almost hear him sing that, Ain't No Sunshine. In the middle of this tune, he sings I Know, and he sings it 26 times in a row. I know, I know, I know, I know. Each one of those I knows is 3/8 notes long, and each bar is 4. And so there's this sort of turning, and every 4 I knows he's sort of back on beat. And it's get this sense of rhythmic sort of instability from that. In the opening of Strauss's Till Eulenspiegel's Merry Pranks, there's a 7-beat phrase played by the horn. But the piece is in 6/8 time, and so the 7-beat phrase in 6/8 time, it sort of is unstable like that, and you need 20 or 42 notes before it repeats again. It's actually quite a prank to play at the beginning of a tune called Somebody's Merry Pranks. In Messiaen's Quartet for the End of Time, we probably have the most extreme example that I know of. Messiaen writes competing patterns that are 17 and 29 notes long. If you think about those, 17 and 29 notes long, it's going to take 493 notes before you get back to the beginning of this pattern again. It's going to take essentially until the end of time. So I want to be clear about the main point from today. Everywhere, songwriters are adding interest to their pieces with rhythmic patterns that give us a sense of turning and finally resolving. Now, musicians tend to think about and understand the tension in resolving, and they're not so much thinking about the mathematics behind it. And that's the main point for today. But I want to end with a little bit of a mathemusical sort of coda. We can use basic rhythms, note lengths, to do some really interesting mathematics. And here's a question that we can actually answer, a mathematical question that we can answer with musical notation. So here's the question. Let's look at the sum 1/2 plus a quarter plus an eighth plus a 16th plus a 32nd plus a 64th, on and on and on. Just keep going with that. Now you might think, and many have, including many of my students, that if you keep adding positive numbers, well, you keep adding positive things. That sum has to go to infinity. After all, you just keep getting bigger and bigger and bigger. You must be going toward infinity. Somewhat unexpectedly, I think, the series converges. It actually adds to 1. If you go all the way to infinity, if you keep adding numbers like this forever, you get 1. And we can prove it with rhythms. So let's look at this musical proof. So let's think about writing a measure of music in 4/4 time. That's 4 quarter notes per measure. And let's start out with just a whole note. A whole note takes 4 beats. And so we have one measure. Mathematically, we have one note that has 4 beats, and that equals one measure. So it's just 1 equals 1. Now replace that whole note with 2 half notes. Those are 2 beats each. We still have one whole measure, but now mathematically, we're looking at 2 half notes. That's half plus a half equals 1 measure. Now replace the second half note with 2 quarter notes. Those are 1 beat each. We still have one whole measure, but now if you think about it mathematically, we have half plus a quarter, and that equals 1. Replace the second quarter note with 2 eighth notes, each 1/2 of a beat long. And we still have one measure, but now mathematically we have 1/2 plus a fourth plus an eighth equals 1. Replace the second eighth note with 2 16th notes, each one of those is a quarter of a beat. We still have a whole measure, but now we have 1/2 plus a fourth plus an eighth plus a 16th equals 1. Let's just keep going with this pattern and see where it leads us. Each time we keep taking the last note, replacing it with 2 notes, each of which is half as long as the one we replaced. That leaves the total length of the rhythm exactly the same. It's always just 1 measure long. But what happens if we do this infinitely, forever? Now, musically, if you wanted to do this, you'd have to play an infinite number of notes, each half the length of the previous one. But if you look at it mathematically, we would be proving that 1/2 plus a fourth plus an eighth plus a 16th plus a 32nd plus a 64th, on and on to infinity, equals 1. Now mathematically, this is called a geometric series. Each term is equal to the previous one times a fixed constant. In this case, it's 1/2. These geometric series turn out to be incredibly important, and they arise in lots of different applications, including, interestingly, your home mortgage and how it's amortized. So I hope you've enjoyed this little mathemusical coda and today's lecture on rhythm. Now that we have pitch, we have scales, we've done chords, and now we've done rhythm, now we're ready to write some really interesting music. So next time we're going to talk about musical and mathematical transformations and how they're used in compositions, and especially in Bach. Thanks for joining us.